Hi everyone. Thank you everyone for coming today. I'm Quan Nguyen from Carnegie Mellon University. Today I'm going to talk about our approach that incorporate gate library and control barrier function to address the problem of dynamic walking on a stepping stone. To motivate the problem, I would like to mention the W price that has the cost of obstacle over 10 kilometers. And one of them is the stepping stone task. And the W price also lists a set of stepping stones that have the step length vary from 35 to 99 centimeters with a precision of 5 centimeters. So please remember this number for now. I will come back with them later in our result. So you may know that in DABA robotics challenge, some robot can overcome this rough terrain course. However, with the W price course, we will definitely need to improve the performance of the robot because we need a wider range of step length, we need faster walking speed, and we need the walking to be more energy efficient. In order to give you a hint about what we try to solve, I would like to show you here a preview of what we can achieve using our approach. Okay, so in the next slide, I'm going to explain briefly how do we develop our controller to achieve this performance. So firstly, with the problem of walking on flat ground, we will design a periodic walking gate using optimization that gives us the gate parameter alpha. And we then do input-output linearization controller to track the desired gate. However, since our gate is periodic, it will give us a fixed step length. For example, our gate have a step length of 50 centimeters. Because the gate is periodic, the step length is always fixed and it's always 50 centimeters. However, in the problem of stepping stone, we want to have a different step length. Then we can have a gate library that contains different gates with different step length. For example, we can have two more gates that have a step length of 30 and 70 centimeters. However, because the gate library is limited or the number of gates is limited, we cannot have an arbitrary step length in between. For example, if we want to have a step length of 37 or 64 centimeters, we cannot use gate library to achieve it. So in order to do that in our method, from the desired step length, we use the gate interpolation so that we're gonna have the new gate parameter alpha gonna be the function of the desired step length of the next step. So with gate library and gate interpolation, we can have a new gate with a random step length. But because each gate itself still periodic, so it means that they still have a fixed step length. So, but the problem that in the problem of stepping stone, we want to switch between two different gates. So, for example, if we want to switch from the gate have a 37 to 64 centimeter, so we're gonna face some problem of step transition issue. So in our method, in order to solve this problem, instead of using input-output linearization controller, we're gonna use CBF or control barrier function controller to handle the problem of step transition. Okay, so I'm going to explain more detail about our gate library and gate interpolation. So let's say we have a gate 1 and gate 2 that have step length L1 and L2 already available in the gate library. Now we want to have a new gate that have the step length L design in between L1 and L2. So our solution is that we're gonna do gate interpolation to get the new gate parameter alpha D that represents the desired step length LD. And we need to notice that the L1 and L2 gate already available on the gate library. And we're gonna do gate interpolation to get the new gate parameter for the desired step length. So now the gate library can offer a new gate with for different desired step length. However, the gate is designed to be periodic. So again, we're gonna face a lot of problem with the step transition issue because when we want to switch from two different gates, the gate is no longer periodic. So again, this is some step transition issues that I've mentioned before. And in our method, we use control barrier function method to handle this step transition. Now I will present how do we guarantee full step placement in our controller. So let's say we want our robot to step onto this stone location. So in our method, we're gonna maintain the swing foot position to be inside this circle O1 so that we can guarantee that the step length on way less or equal to L max. And similarly, we want to maintain the swing foot position to be outside this circle O2 so that we can guarantee the step length on way greater or equal to L min. And when we combine these two constraints, we can guarantee the full step placement constraint. And an important thing is that with this constraint, we also guarantee the swing foot clearance, because you can see that the swing foot position on way above this circle O2, therefore we can guarantee the swing foot clearance. And we also need to notice that the constraints are enforced using a real-time feedback controller, not an offline optimization. So the controller we use is a CBF COF QP controller, where COF stands for control Lyapunov function and CBF stands for control barrier function. So firstly, in our controller, in order to guarantee the stability, we want to drive the control output eta to 0. So in our method, we're gonna define a control Lyapunov function, for example, this quadratic form. And now if we can design a control output that can satisfy this COF condition, we're gonna drive the Lyapunov function go to 0 exponentially, and therefore we can drive the control output eta go to 0 exponentially. And on this side, with the control barrier function, we want to guarantee the state-dependent constraint be bias greater or equal to 0. And in our method, we're gonna define this CBF condition. And if we satisfy this condition, we're gonna guarantee that the CBF condition, we're gonna guarantee this constraint. And we need to notice that the CIF condition and the CBF condition are very similar. The only difference is just the site. And with this CBF condition, we can guarantee that the BFI is gonna be upper bounded by an exponential function, and therefore we call it an exponential CBF. And based on this condition, we can use quadratic program to solve the control input due with subject to this condition. And in the QP, we can also incorporate input saturation and friction constraint in the QP. And this QP is solved online in real time as a feedback controller. So again, in our method, in the high level control, we update a new gate for every walking step. So this dot light is the discrete time signal, or we update it for every walking step. And in the low level control, as a real time feedback controller, we use a CBF controller to handle step transition issue. And you can see here that in our controller, we just need to know about one step ahead knowledge, or we just need to know about the desired step length for every walking step. So this is the simulation result using our proposed approach. So in the first case, we generally generate the stepping stone from 10 to 100 centimeters, and we can achieve very small stone size of 2 centimeters, or we have a very precise step placement. And in second case, we manually pick the worst case when the step length is 15 or 95 centimeters. Okay. So come back to the W price, the stepping stones that have a step length of 35 to 99 centimeters with a precision of 5 centimeters. In our simulation, we can have a larger range of step length from 10 to 100 centimeters with a much more accurate stepping full step placement. However, I'm not going to say that we are done with the W price, because even in the simulation, because there's still some more interesting challenge that we need to address. in order to get into this point, because we need to, for example, in this picture, you can see that the W apply requires to change the step height in the first and the last step. And we also need to address constraint on single block toppling, and in fact, it's still a 3D walking. And we are still working on experiment, but I would like to show here one preliminary result. As you can see here, in this experiment, we change the step length of the robot for every walking step. So this is a very small step, just small step, last step. Okay. So in conclusion, our method can handle a wide range of step length. We can have a precise footstep placement with the precision of 1 centimeter. We can, at the same time, we can also handle fast dynamic walking with the average speed of 1 meter per second. And in our method, we require only 1 step ahead knowledge. However, we still have a dirty laundry need to be cleaned up for sure. So in our problem, we just handle 2D walking. And because our controller based on the nonlinear model, we require an accurate model. And we didn't have feedback of the swing foot position in the controller. So we may require an accurate estimation of the swing foot position. And when we run the multiple run for the stepping stone, we can see that we still have some failure case in the simulation. So in the future, we may want to extend the problem to 3D stepping stone and try to improve the experiment. Okay, thank you.
So Aaron Ames is our first responder.
Nice work. So you interpolate between the parameters in the gate library, right, to get this continuum of gates. But then that requires your online optimization to handle, you know, all those switching between gates. You can get torque spiking, so you're going to torque bound, which will remove guarantees in your CLF. So why don't you instead create a graph where each node is gates, and then you do interpolation between the zero dynamics to ensure feasibility of the physical constraints at the gate level. And then that will make the QP more solvable.
So,
Did you get that? So you're creating a continuum of gates, right? And you're interpolating between parameters.
Okay.
But when you switch, you're going to have torque spikes, right? Because you're going to be switching between these gates. So instead, create a graph. Each node in the graph is a gate, and then you interpolate between the zero dynamics. Then you won't be switching between periodic orbits. You'll be nicely, smoothly going between all these different gates, right? So you create a feasibility graph. And then what that will do is require less out of the QP, which will make it more feasible, right? Have you thought about doing this? So having a more physically correct gate library, so you don't have to leverage the QP so much, because when you leverage the QP, you have to relax the CLF.
So,
does that make sense?
Yep. So do you mean that instead of using periodic gate, we may want to use no?
Yeah, I'm saying you have a gates, and then you interpolate between the zero dynamics to switch between them in a more principled way than just interpolating and switching randomly, right? Does that make sense? So you get more physical constraints at the gate library level, because now your gate library is, instead of a continuum, one-dimensional, you make it a two-dimensional graph.
Okay.
I'm going to interrupt and just say, Aaron, you should write a paper on that. And actually, if there's time for one more question, I'll let Aaron work it out with Quan later.
Okay, well, that's a good idea.
Okay. Any other questions? Yes.
The sub-question, Aaron, is what happens? How often does your QP go infeasible? And can you detect? I mean, can you detect that? You're making some guarantee about minimum step size, maximum step size, but those guarantees depend on the QP being feasible. And how do we know that the QP is going to be feasible?
So basically, when so in our prior work, when we do one gate only, we're gonna have the limited step length. So when we have a gate library, we gonna have we can increase the feasibility of the QP. However, the problem that when we in larger step length, for example, we can. The problem is that so when we switch between two very different gates, for example, we can have have a predict walking up 100 centimeter. However, when we switch from 10 to 100 centimeters, it's going to be very tricky, and the QP can be infeasible in this case. So this is a problem of switching. So
okay, let's thank our speaker again. And